today the subject is linear models, and as I mentioned at the beginning, this is out of sequence. If I was following the logical sequence, I would go immediately to the theory and take the capital M, which takes care of the finite case, and then generalize it to the more general case. However, as I mentioned, I decided to give you something concrete and practical to work with early on, and then we will go back to the theory after that. So the linear model is one of the most important models in machine learning. And what we are going to do in this lecture, we are going to start with a practical data set that we are going to use over and over in this class. And then if you remember the perceptron that we introduced in the first lecture, the perceptron is a linear model. So here is the sequence of the lecture. We are going to take the perceptron and generalize it to non-separable data. Okay? That's a relief because we already admitted that separable data is very rare, and we would like to see what will happen when we have non-separable data. Then we are going to generalize this further to the case where the target function is not a binary classification function, but a real valued function. That also is a very important generalization, and linear regression, as you will see, is one of the most important techniques that is applied mostly in statistics and economics, and also in machine learning. Finally, as if we didn't do enough generalization already, we are going to take this and generalize it to a nonlinear case. Okay? All in a day's work, all in one lecture. It's a pretty simple model, and at the end of the lecture, you will be able to actually deal with very general situations. And you may ask yourself, why am I calling the lecture linear model when I'm going to talk about nonlinear transformation? Well, you realize that nonlinear transformation remains within the realm of linear models. That's not obvious. We will see how that materializes. So that's the plan. Okay, now let's look at a real data set that we are going to use and will going to be available to you to try different ideas are. And it's very important to try your ideas on real data, regardless of how sure you are when you have a sort of a toy data set that you generate. You should always go for real data sets and see how the system that you thought of performs in reality. So here is the data set. It comes from zip codes in the postal office. So people write the zip code, and you extract individual characters, individual digits. And you would like to take the image, which happens to be 16 by 16 gray level pixels, and be able to decipher what is the number in it. Okay? Well, that looks easy, except that people write digits in so many different ways. And if you look at it, there will be some cases like this fellow. Is this a 1 or a 7? Okay. Is this a 0 or an 8? Okay. So you can see that there is a problem. Okay. And indeed, if you get a human operator to actually read these things and classify them, they will probably be making an error of about 2.5%. Okay. And we would like to see if machine learning can, at least equal that, which means that we can automate the process, or maybe beat that. Okay. So this is a data set that we are going to work with. So let's look at it a little bit more closely to see how we input it to our algorithm. We have one algorithm so far, which is the perceptron learning algorithm. We are going to try on this, and then we are going to generalize it a little bit. Okay. So the first item is the question of input representation. What do I mean? Okay, this is your input, the raw input, if you will. Okay? Now, this is 16 pixels by 16 pixels, so there are 256 real numbers in that input. Okay? So if you look at the raw input x, this would be x1, x2, x3, and x256. That's a very long input to encode such a simple object. Okay? And we add our mandatory x0. Remember, in linear models, we have this constant coordinate, x0 equals 1, we add in order to take care of the threshold. So this will always be in the background whether we mention it or not. So if you take this raw input and try the perceptron directly on it, you realize that the linear model in this case, which has a bunch of parameters, has really just too many parameters. Okay? It has 257 parameters. If you are working in a 257-dimensional space, that is a huge space. And the poor algorithm is trying to simultaneously determine the values of all of these W's based on your set. Okay? So the idea of input representation is to simplify the algorithm's life. Okay? we know something about the problem. We know that it's not really the individual pixels that matter and whatnot. You can probably extract some features from the inputs and then give those to the learning algorithm and let the learning algorithm figure out the pattern. Okay, so this gives us the idea of features. What are features? Well, you extract the useful information, and as a suggestion, very simple one, let's say that in this particular case, instead of giving the raw input with all of the pixel values, you extract some descriptors of what the image is like. So for instance, you look at this, depending on whether this is the digit 8 or the digit 1, etc., there is a question of the intensity, average intensity. 1 doesn't have too many black pixels, 8 has a lot, 5 has some, okay? So if you simply add up the intensity of all the pixels, you probably will get a number that is related to the identity. It doesn't uniquely determine it, but it's related. It's a higher level representation of the raw information there. Same as symmetry. If you think of the digit 1, 1 will be symmetric. If you flip it upside down or you flip it right and left, you will get something that overlaps significantly with it, okay? So you can also define a symmetry measure, which means that you take the symmetric difference between something and its flipped versions, and you see what you get. If something is symmetric, things will cancel because it's symmetric, you will get a very small value. And if something is not symmetric, let's say like the 5, you will get lots of values in the symmetric difference, and you will get high value for that. So what you are measuring is the anti-symmetry. You take the negative of that, and you get the symmetry. So you get another guy, which is the symmetry. So now x1 is the intensity variable, x2 is the symmetry variable, okay? Now, admittedly, you have lost information in that process, okay? But the chances are you lost as much irrelevant information as relevant information. So this is a pretty good representation of the input as far as the learning algorithm is concerned. And you went from 257 dimensional to 3-dimensional. Okay? That's a pretty good situation, and you probably realize that having 257 parameters is bad news for generalization if you extrapolate from what we said. Okay? Having 3 is a much better situation. So this is what we are going to work with. Okay. So when you take the linear model in this case, you just have W0, W1, and W2, and that's what the perceptron algorithm, for example, needs to use, to determine. Okay. So now let's look at the illustration of these features. Okay, you have these as your inputs, and x1 is the intensity, x2 is the symmetry. What do they look like? They look like this. So this is a scatter diagram. Every point here is a data point. It's one of the digits, one of the images you have. And I'm taking the simple case of just distinguishing the 1s from the 5s. So I'm only taking digits that are 1s or 5s. And you can always take other digits versus each other and then combine the decision. So if you can solve this unit problem, you can generalize it to the other problem. Okay, so when you put all the 1s and all the 5s in a scatter diagram, you realize, for example, that the intensity on the 5 is usually more than the intensity on the 1s. Okay, there are more pixels occupied by the 5s than the 1s. So this is the coordinate, which is the intensity, and indeed, the red guys, which happen to be the 5s, are tilted a little bit more to the right, corresponding to the intensity. If you look at the other coordinate, which is symmetry, the 1 is often more symmetric than the 5. Therefore, the guys that happen to be the 1s, that are the blue, tend to be more higher on the vertical coordinate. Okay? And just by these two coordinates, you already see that this is almost linearly separable. Not quite, but it's separable enough that if you sort of pass a boundary here, you will be getting most of them right. Now, you realize that it's impossible really to ask to get all of them right because, believe it or not, this fellow is a 5, at least meant to be a 5 by the guy who wrote it. Okay? So we have to accept the fact that there will be stuff that is completely undoable. Okay? And we will accept an error. It's not a 0 error, but hopefully it's a small error. Okay? So this is what the features look like.